Hello and welcome to the MOOC on optical communications. In the last module we were discussing how to increase the spectral efficiency. We will continue the discussion and introduce an additional way of increasing the spectral efficiency. Okay. So, we have already looked at one method of increasing spectral efficiency, that is single carrier plus higher order modulation. Okay. If you have a DWDM channel of 200 bands and each band can then be utilizing a 16 QAM or a 64 QAM, then the overall spectral efficiency will also increase. Okay. The catch here is that, let us look at first the BPSK situation and then come back to the other approach over here. With BPSK, what are the symbols that we have? We have one symbol which is symbol 1, and then you have a symbol which is 0, and these two are placed such that their normalized average power or average energy is equal to 1. Okay. So, they are placed as far as apart is possible. The way to distinguish between a 1 symbol and a 0 symbol for the BPSK is that if your received signal for some reason happens to be in this region of operation or in this region of the signal space where I have I and Q, you look at the distance between these 2 points. Okay. Clearly, this blue dot or the blue received symbol is closer to this 1 rather than to 0, and therefore, you can declare this one as bit 1. You can see that this entire region will then be declared as bit 1, because signal falling anywhere within this region will be closer to 1 than it would be equal to 0, and obviously anything that would fall within this region will be allotted bit 0. But interestingly, if let us say you have a BPSK transmission and then you have some phase noise. Okay. What would the phase noise do to the BPSK signal is that it kind of starts to rotate the constellation points. Okay. So, the received signal can be lying anywhere on this circle depending on how strong your phase noise is, it can lie anywhere on this circle. Okay. One can see that as to completely cover the circle means that the phase noise has to be large. If the phase noise is not very large, then it would be only over one particular section. Okay. So, let us say over this segment your received signal can lie anywhere, but still notice that you are not making any errors here. Okay. If you add some ASC noise around that, then this would be the situation that you have. Okay. So, you have some AC noise coming from the amplifiers, coming from the interaction of amplifiers with everything else that we will look at. Your received signals can be anywhere here, and of course, they can anywhere be rotated by this particular value. Okay. So, you see that with this received constellation you are still not making much of an error. Okay. And primarily the reason for this that is happening is because the phase noise is still manageable. The phase noise is over here, it is still manageable because it is only covering one segment over here. Okay. If the received signal has to go to the other region, okay, wherein they are not supposed to go, right, then the phase noise variance or the phase noise RMS value must be greater than 90 degrees, greater than or equal to 90 degrees. So, this 90 degree is the margin of error that we have, okay, for BPSK signals. So, with BPSK signals the margin of error is 90 degrees, and this is a pretty large margin that you are going to get. Suppose you have received the signal. Okay. So, received signal is the photocurrent, which I am representing this as RK. This received signal will be sum of the signal that you have actually transmitted, which is SK, plus you have some noise NK, right. And if you look at when you are going to get this an error, when this RK, so what would be the probability of mistaking the received sample as 0 when you have transmitted a 1 would be when this RK becomes less than 0, right. So, if this particular scenario happens, then you can see that the received signal RK, when its value becomes less than 0, then it would be declared as a 0, and this would clearly be the error that you are looking for. Otherwise, you are on the side. So, as long as this part is okay, right, you are in this particular area, you would not have made an error, but the moment you go from there to here, you would have made an error, and that error would happen when RK is less than 0. Okay. If you look at the coherent receiver output, right, the photocurrent that you are going to obtain would have the signal component, right. What would be the signal component there? It is 2 times square root of PS PLO, and in this case PS will be the same value. So, whatever the PR, the received signal value for both 1 as well as 0, because in case of both 1 as well as 0, you are transmitting a certain amplitude sinusoidal signal to the receiver, both carrying the same average power of PS, okay, or carrying the same power of PS. Okay. So, the received signal will be 2 square root PS PLO. I am of course assuming that this responsivity R is equal to 1 in this case, and then you have cos of theta of t, where theta of t is the phase difference between the signal, that is the signal field which is Es of t, and the local oscillator field which we are assuming to be having 0 phase. Okay. So, this phase difference is cos theta of t, and clearly this theta of t must correspond to either theta 0 or theta 1, theta 0 when you have transmitted bit 0 and theta 1 when you have transmitted a bit 1. Okay. Plus there will be short noise terms. If you were to sample this signal to generate your RK, you see that this would be square root of 2 PS PLO, and assume now that you have transmitted a bit 1. So, when you have transmitted bit 1, theta 1 must be equal to 0, theta 0 of course is equal to pi when you are transmitting bit 0. So, this would be 2 square root PS PLO, cos of 0 will be 1, plus whatever the short noise sample that you are going to get. Okay. If this received signal, because of the noise that you have, which is mostly limited by the LO short noise, that we are assuming that this is LO which is giving you the largest component of the noise, then if this combination is less than 0, then there is a probability that you would have mistaken the received signal as a bit 0, right. Although you have transmitted 1, you are going to declare the bit as a 1, which would be in error, right. So, you can rearrange this equation and then say the condition for this to happen is when the noise actually falls below this minus square root of 2 PS PLO, and then you can integrate and do the appropriate calculation to find out what would be the probability of 0 to obtain a 1, and express all this in terms of the Q factor. Okay. So, or the Q function. The Q factor for the PSK system, for the BPSK system, can be defined by looking at I1 minus I0 by sigma 0 plus sigma 1, and we know that I0 will be equal to minus I1, right. So, you get 2 times I1 divided by 2 times sigma 1, because the noise for 0 and noise for 1 in the LO short noise limited case will be approximately equal, okay, and I0 will be equal to minus I1, that is when you transmit a bit 0 you will get minus of the current, right, the amplitude would be negative. So, you get minus I1, and 2 cancels over here, and the Q factor simply becomes I1 by sigma 1. Contrast this to the Q factor for on off keying. Okay. With the on off keying, I0 was 0, sigma 0 was approximately sigma 1, and your the Q factor would have been I1 divided by 2 sigma 1. Okay. So, you can already see that on off keying is minus 3 dB worse compared to the BPSK system. Okay. So, if you look at the Q factor versus the bit error rate, you will see that as the Q factor increases, the bit error rate drops out. The first thing would be the highest sensitivity would be for BPSK, then you get a sensitivity which is 3 dB degraded for the on off keying. Okay. This is all nice for a BPSK system. Okay. I am not going to look at the expressions for this probability of error, they are not very important, but this graph is very interesting, right. So, BPSK seems to be performing better, and the margin of the phase error in this case is about 90 degrees, which is very interesting. Now, you go to from BPSK you go to this 4 PSK. Here the constellation points are located here, and then the decision regions will now be located at these points, right. So, if my received signal happens to lie within this particular region, then anywhere if it lies in this region, then I will declare that one as this bit sequence. Okay. On the other hand, if my received sequence lies anywhere over here, then I will declare this one as corresponding to this particular bit sequence. Similarly, you have additional 2 regions as well. Okay. You can calculate the error factors over here, but what is interesting to observe is that if only phase noise is present, then the phase noise margin of error would now have been reduced from 90 degrees to 45 degrees. Okay. This is very important. So, you are now cannot go more than 90 degrees. So, 22.5 degrees on this side, 22.5 degrees on this side, I think that is what 45 by 2 is, and roughly you are going to get 45 degrees up here. Okay. If you now start going to higher order modulation, for example, we talked about an 8 array PSK modulation, right. So, you can see very clearly that the decision regions corresponding to this would then be even more closely spaced. Okay, so this is one more decision region, so you are going to get, that should have been over here. But the point is to note that the noise margin or the phase noise margin starts to decrease again here, right. So, from 45 it should become now 25.5 degrees. So, as you start packing in more and more number of constellation points, the allowable phase noise margin degrades. Now, if you say my phase noise margin should be just 1 degree, there is actually a relationship between the phase noise variance and the bit rate as well as the line width, right. For the same bit rate RB, okay, the phase noise variance is given by 2 pi delta nu divided by RB. Okay. So, if you fix RB then and say this should be 1 degrees versus say 45 degrees, clearly the constraint that you are going to get will be on the line width of the laser. Okay. It would then become very difficult to fabricate lasers with line widths as small as what we are looking for. Okay. For a case of RB equal to 100 Gbps, I will leave this as an exercise for you to find out what would be the variance or what would be the line width delta nu, such that the margin of error is 45 degrees and the margin of error is 1 degrees, and you will be surprised to see that the kind of delta nu that is required for 1 degree phase margin or the phase noise variance would be very tight, and to achieve such low line widths is very expensive. So, it is actually very expensive thing to realize this 1 degree variance kind of a system. Okay. So, the drawback for increasing the spectral efficiency of a single carrier system is that as you start packing in more and more number of points, okay, the allowable noise margin and the system specification also starts to increase. Also, with 1 degree variance that we have assumed for the phase noise, okay, or we want for the phase noise, the main drawback will again apart from of course constructing the laser, the other major drawback will be that how are you going to synchronize the transmitter and the receiver if the margin of error is just 1 degree out there, right. So, that is the kind of trouble that one has to look for when you go to higher order modulation, but this has not stopped people from going to higher order modulation and up to 64 QAM. The only thing is the complexity of the receiver starts to increase dramatically. Before we go to the other approach, a quick way, so we were looking at how to implement a 8 array PSK system. So, if we have already not looked at how to implement an 8 array PSK system, all you have to do is to take 3 phase modulators, call them as PM1, PM2 and PM3, connect them in cascade. This is one possible realization I am talking about, and send in the bits here B2, B1 and B0. This is for a straight binary encoding. If you send in D2, D1 and D0, which stand for the gray encoded symbols, then that kind of headache is up to you. Okay. You configure the first phase modulator to give you phases from 0 to pi. Remember how to do this one, this is by sending 0 voltage signal. To obtain a pi phase shift, you have to send in V pi. Okay. Similarly, you configure this phase modulator to give you 0 and pi by 2, this one to give you 0 and pi by 4. Okay. And you now look at what kind of constellations I am going to get in the IQ plane, okay, when this B2 is equal to 0. So, with B2 equal to 0, the total possible phases that I am going to get here is 0 when both of them are 0 0, you get pi by 4, you get pi by 2 and you get pi by 2 plus pi by 4. Okay. When bit B2 is equal to 1, to these phases you have to add pi. So, you get pi plus 0, pi plus pi by 4, okay, pi plus pi by 2 and pi plus pi by 2 plus pi by 4. Let us mark these points. 0 phase goes here, pi by phase 4 phase goes over there, pi by 2 goes here, they all have the same amplitude. Okay. Although it might not look very nice as a circle, you have to assume that I am putting everything on a circle. Pi by 2 plus pi by 4 is this one. Okay. So, what are the bits that you are going to get? This is for 0 0, this is for 0 1, this is for 1 0 and this is for 1 1. Okay. Next, what do I have? I have to translate everything by a value of pi or rotate everything by a value of pi. So, 0 becomes this symbol, this one goes through here, this one goes through here, this one goes to this side. Okay. You can now complete, if you are interested, you can complete a circle over here and see that they all have to lie on a circle. Unfortunately, this is not a very nice circle, but the corresponding bits that you are going to get are, so 0 0, this would be 1 0, this is 3 bits, right, because you have actually 3 bits to work with. So, you have 0 0 0. So, these two are B2 B1 and B0. You have 0 which is B2, 0 1 0 1 0 0 1 1, and then you get 1 0 0 1 0 1 1 1 0 and 1 1 1. Okay. So, this is how you generate an 8 array system. Now, to generate a 16 star QAM, okay, all you have to do is take a 8 array PSK system over here, okay, and then have an intensity modulator. To this 8 array PSK you supply B3, B2 and B1, okay. To this intensity modulator you supply B0, B0 being the least significant bit, okay. So, you supply the least significant bit, and what you would essentially generate is one 8 array PSK correspondingly defined by B3, B2 and B1, and the same 8 array PSK, but this time with a different amplitude, okay. And that would be, so any point here is all this with B0 equal to 0, and the points over here will be B3, B2, B1 with B0 equal to 1, okay. So, this is with B0 equal to 0. So, the inner circle with B0 equal to 0, outer circle with B0 equal to 1, and you will be able to generate the 16 star QAM. Additional types of generation including IQ modulators is all not important for our module here. So, we are not going to discuss that. Having looked at one way of improving the system performance, okay, in terms of the spectral efficiency, we will now look at an additional or a different type of an approach. This approach is called as multi-carrier modulator approach, or in earlier situation it was also called as sub-carrier multiplexing approach, okay. These two are not exactly the same, but for our purposes they can be considered to be almost the same. What we do with multi-carrier modulation is that, suppose I have some symbols, okay. So, let us call these symbols as x0, x1, x2 all the way up to xn minus 1. So, there are these n symbols, these are all complex symbols that you have. So, if you are looking at BPSK modulation, then x0 will be real, of course, because it is plus or minus 1, but if you are looking at a QPSK, then x0, x1, x2, any of these can come from 1 plus j, you have minus 1 plus j, you have 1 minus j, then you have minus 1 minus j, okay. So, this can be any of these x0, x1, x2 all the way up to xn minus 1 can be any of these for the QPSK modulation, and for additional modulations they can be any of the other complex numbers, okay. What we do is, over a particular bit period, over the symbol period, so let us say 0 to t, okay, let us multiply each of these symbols with a bank of modulators. So, let us say I take this x0, multiply it with by e power j 2 pi f0 t, multiply x1 with another signal, sinusoidal signal, complex sinusoidal signal of course, with 2 power e power j 2 pi f1 t, and then you have x2 e power j 2 pi f2 t, and so on. At the kth time you have xk e power j 2 pi fkt, okay. Finally, you have the last one as xn minus 1 e power j 2 pi fn minus 1 t, okay, where these frequency components f0, f1, f2 are all equally spaced, okay. So, this is f0, this is f1, the spacing between them is called as the subcarrier spacing. These f0, f1s are all called as the subcarriers, the last one is at fn minus 1. So, clearly the kth subcarrier frequency is given by f0 plus k into delta f, k goes from 0, 1 all the way up to n minus 1. Now that you have multiplied all these signals along with their bank of modulators, what you do is you sum all of them, okay. You sum and call the resulting signal as x of t. So, this x of t is what is called as a multi-carrier signal, and in short we can write this as sum over k equals 0 to n minus 1 xk e power j 2 pi fkt. Now, you can question, how am I going to receive this x of t? So, after this you transmit it to the receiver side, okay. So, you can say, how do I obtain this xk? Well, you can do one thing, take this x of t and multiply it with e power minus j 2 pi flt, where fl is one of the frequency components that you have, okay. Integrate over one period and average it by making it 1 by t, okay. If you carry out this integral by putting x of t inside, what you end up is the integral okay, apart from whatever the summation signs that you are going to get, the integral will be e to the power j 2 pi f0 t e to the power j 2 pi k minus L delta f into t, okay, integrated over dt. So, if this k is equal to L, then this would be equal to 1. This e to the power j 2 pi f0 t with f0 is normally taken to be equal to 0 will then give you t by t will be equal to 1, and simply what you are going to get here after doing all this integration will be the data symbol xl. Okay. For this to happen, of course, you need to have only when k is equal to L, and when k is not equal to L, this integral should go to 0, and that will happen when you look at the orthogonality of the basis signals, which are this e to the power j 2 pi f k t, and recall that if you take this integral e to the power j 2 pi k minus L delta f t, okay, and take delta f, this integral is from dt. So, if you take delta f is equal to 1 by t and then consider k minus L is not equal to 0 and rather it is equal to m, where m is some integer, then this would be an integration of sinusoidal signal which has m cycles inside one period, okay. And because a sinusoidal signal having m cycles within one period will integrate out to 0, when k is not equal to L, okay, this result will be equal to 0, okay. So, clearly you can recover what x of L is. However, that is not as simple as we talk about. So, we go back to what x of t is and recall x of t, that would be equal to k equal to 0 to n minus 1 x k e power j 2 pi. I know what is f k, right? F k is now given by k into delta f, but delta f is nothing but 1 by t. So, therefore, I can rewrite this as 2 pi k divided by t and small t, okay. So, this is the multi-carrier signal that you have, okay. Now, do one thing, instead of taking this continuous signal x of t, you sample this, okay. You sample this at the nth sampling time, which is given by n t s, and you take this sampling time t s as the symbol period t divided by n, okay. So, you take your symbol time t and then you break it up into n equal parts, and when you break them into n equal parts, you are generating t s spaced samples, okay, and you look at what happens to x of t there. So, the sample signals x of t n, which is given by x of n t s and further compressed in notation writing as x of n, is given by summation k equal to 0 to n minus 1 x k, there is no change there, but in place of t you have to go to the discrete time, which is n t s, which is n into capital T by n. There is a t in the denominator here, there is a t here, those t will cancel out, what you get is e power j 2 pi k n by n. And if you know your DSP, then you know very well what is this expression. This is nothing but IDFT of the sequence xk, okay. IDFT can be computationally implemented using IFFT. So, what you get as the time samples that you are transmitting from transmitter to the receiver are simply the IFFT of the sequence, okay. When these samples go through the fiber, okay, the fiber impulse response will convolve with the samples of the signal x of n, and what you get would be the output sequence y of n. And to these y of n, if you now apply the FFT operation, and assuming everything has gone okay with the, we will see what those things in the next module, but if everything else goes correctly, then after taking the FFT you are able to extract the data sequence xk, okay. So, at the transmitter you start with the symbols, okay, and then you start with the symbols x0, x1 all the way up to xn minus 1. You convert them into a parallel form using a serial to parallel conversion or a serial to parallel converter. You get x0, x1 all the way up to xn minus 1. To this you can connect, or you take the IFFT of this, okay, and then take it through a DAC, which is digital to analog converter, to obtain the continuous waveform or the approximate continuous waveform, and then multiply it by some e to the power j 2 pi f0 t to up convert it onto the RF domain, and further up convert it using an MZM onto the optical domain, wherein to the MZM you are going to give a laser diode and then transmit it through the fiber. So, this has to be a block called parallel to serial conversion. It can come after DAC or before DAC depending on how you are implementing, but at the receiver side what you have is the signals which are coming in sequence, which would be the samples y of n. Y of n will be x of n convolved with h of n, okay, where h of n is the impulse response of the fiber. You take these samples, okay, y of n. Before you get to this one, you should actually have a photodetector. So from the photodetector, you extract these samples y of n, which would then represent x of n convolved with the impulse response h of n, put them through a serial to parallel converter again. So extract the parallel components, take the FFT of the sequence, and then again convert this FFT into a serial. After FFT you convert this into a serial using a parallel to serial combination, and what you get are the data symbols x0, x1 all the way up to xn minus 1. Okay. This of course assuming that everything in the world has gone right, so that there is no noise, there is no offset, there is no phase error. Okay. We will see all those effects in the next module, but if everything else goes well, okay, this system is able to reproduce your transmitted symbol at the receiver side simply by exploiting the orthogonality of the basis sets, which are the e to the power j 2 pi fkt, the cosine complex sinusoids as the basis functions, and this system is called as orthogonal frequency division multiplexing or OFDM. Okay. OFDM is a special case of multi-carrier modulation. Okay. And for optical communications, the advantage of OFDM is that it can combat the chromatic dispersion in the fiber. So it can easily be or relatively easily one can compensate for the dispersion in the orthogonal frequency division multiplexing. The drawback is that the phase noise has to be still critical here, and any residual phase error or the frequency offset error will be detrimental. But thanks to a lot of work that people have done in the wireless and the RF side for OFDM, one can utilize many of the algorithms that are developed there to mitigate the problems with phase offsets, phase errors, frequency offsets, frequency errors, and any other kind of impairments that OFDM systems go through. An additional disadvantage of OFDM systems is that they are subjected to what is called as a high peak to average power ratio, and because your optical amplifiers, the erbium doped optical amplifiers respond differently when you have one of the bands saturating the power, this could be a little bit of a problem, and there are techniques to avoid this PAPR, or at least to minimize this PAPR, and we will talk about some of those techniques, or just very briefly we are going to mention that in the next module. Okay. So, in the next module we will come back and finish this discussion on OFDM. We have not introduced another very important aspect of OFDM called as cyclic prefix. We will introduce that, complete the discussion of OFDM, and then take up the further impairments that an optical fiber can produce to your signals once the signals are propagating. Thank you very much.